So let's start with the current situation that we want to talk about, which is RNG. And in particular, Philox-based RNG. We're going to just focus on that because that's what most of our systems want to use. For context, we have multiple systems that have some issues with our RNG and want to do some changes. In particular, we have Torch compile that wants to be able for the compiled graph to generate the same thing as the non-compiled graph for once, and also want this to be a functional API so that it fits well within other compiler passes. Two, we have distributed people that are looking into getting a distributed way, basically, to generate random numbers. And in particular, the idea is like within the D-tensor world, when you sample or like fill a D-tensor with a uniform distribution, you want that to also work if your D-tensor is on multiple machines. And you would like for it to as well give you the same result, whether you sample it locally or remotely. And finally, there's another one that is a bit more up in the air, and that Richard can give more details, which is related to PyTorch. So our current RNG API being stateful and being what it is very not easy to use in the context of functional transforms, in particular VMAP. And so it has been a pain for a while. And so there are some proposals to get a more user-friendly RNG API within the context of Torch.func. And so that is also something that we are looking into here. As you realize from what Olav was saying, basically one of the cornerstone of all of these things is that, well, we need a functional RNG API. And so that one we are pretty set on doing. Basically, we will need a functional RNG API, and then each of these different components will need to do a bunch of work to make sure that they integrate with that RNG API. So that is the high level, this is what we're doing kind of presentation. Any question on that? Yes, Klaus.
Are you going to change rand also, or just rand?
This is introducing a new API. This is not changing Torch.rand.
Will they behave the same? Like if I use functional Philox RNG versus existing non-functional Philox RNG, will they work the same?
Yes. So there is some guarantee that you can use this functional API to replicate the behavior of eager Torch.rand. Yes, this is what, in particular, Torch compile definitely needs. We definitely need the RNG sampled from within a compiled block or outside of it to be the same.
Are you going to be changing internals or just doing like API movement around?
So a current eager API will not change. There is no plan on that side, no. The controversial question I want to ask is going to be around implementation of the current eager APIs, yes.
Actually, before we get there, I have a sort of related question to Vaz's question. So what I couldn't tell is after we've done all of these proposed changes, when I ask PyTorch for random numbers in eager mode using the old APIs, do I get the same numbers that I did before these changes?
It depends on how we decide on the other thing. So either we leave eager API as is, that's an option. The other option, which is the one we are proposing here, which is the case for changing how we sample, would change the behavior of eager.
Okay.
Sampling.
So to be clear, like basically we would have to put this in blinky lights being like, hey, we changed our RNG algorithm and you won't be able to reproduce your experiments anymore.
Correct.
To be fair, we've already changed our RNG algorithm without blinking lights and nothing happened.
Yeah.
Yeah. They are non-consistent between devices today. They are non-consistent between hardware today, and they are not consistent between PyTorch versions today. So I don't expect the fact that we would change it here to be a problem in any way.
I also have another question, which is, after this change, would it be consistent across hardware?
If we do not change the current internal, no.
I'm saying if we change the eager implementation.
Yes, the proposal here is that we can make all the hardware consistent.
Okay. Sounds good to me.
Any other question before we dive into that one then? Okay. So I'm going to go through the problem of why, what the problem is and why we want to change it quickly. Ed, do we have time to do that, or do you want to go faster?
Let's you've got at least half an hour, I think.
Okay.
But it mostly depends on like how important you think it is for this room to understand the details about what's going on.
Okay, I'll do mid-level. Okay. So I would say one very interesting observation that you can make today, if you sample random numbers on CUDA, is this: that if you set the manual seed, you sample 4 numbers, you sample 4 other numbers, and then you set the manual seed to the same thing and sample 8 numbers. The first 4 do match, the last 4 do not. You know, it is not the end of the world, but it is definitely very surprising. In particular, if you do the same on CPU today, you will get the 8 numbers that are consistent, that are the same, depending on how you set it up.
Would it still hold if you are sampling not 8 numbers, but like 2 to the 24, so that multi-threading on CPU kicks in?
I haven't tried. No, that's fine.
My hypothesis is it doesn't. Same happens probably when CPU switches from non-vectorized implementations to vectorized implementations.
Yeah. So this behavior in particular is a problem for it's not nice, I would say, for Torch compile, because the compile code will not give you the same results. Sorry. We can get the Torch compile code to give you the same result as before because we never do this kind of behavior. But for things like distributed, where we are going to split the sampling from being on one device for the full tensor into multiple devices, each sampling a subset, obviously you can see that we will not be able to get the same result. And in the context of PyTorch, where you do things like, you generate a set of random noise for you generating algorithm, and then you want to regenerate the nth element from that noise to regenerate that particular image. Well, again, this is not something you can do. Very quickly going through why this happens this way is that for a given seed, you can see the Philox algorithm has having this gigantic 2D array of random numbers that we're going to read from. And the way we read from them is as follows. So for example, if you sample 5 elements, and starting with the offset of 0, we're going to sample these 5 elements and move the offset by 4. Meaning that when you sample 5 elements again, this is the 5 elements you're going to sample. On the other hand, if you sample 10 elements, basically these are the ones that you will sample. Very obviously, you can see that if using this algorithm, if you want the 5 last numbers, well, there is no argument you can give to the sampling here to sample these 3 and then these 2. So basically, if we want to get this behavior, it's going to be, we're going to have to change the way we read this array. And the proposal on how we could change reading the array is by saying we're actually going to use a single subsequence and sample everything from that subsequence, with each thread getting as many numbers as it needs. And if you do that, basically, we can just linearize everything. We can pre-compute all these offsets and get the value we want. Yes, Ed?
So my question is back to the first diagram. So how come we moved the offset by 4 for both sampling 5 and 10 random numbers?
Because on CUDA, at least, sampling 1 number at a time is very slow, or at least used to be slow. It's not super clear to me. There are a whole bunch of comments in the code base that say that for performance reasons, we always sample inputs 4 at a time.
Yeah, but no, but I still don't understand because you need to use up more offset when you generate 5 random numbers than 10. Is that not
No,
true?
in this case,
No.
we are first exhausting the whole column rather than the row.
So
So
here you see that if I sample 10 again, I still start from offset 4. The only thing, as Animesh is saying, is that I use more of the column than before. And
so how much do I have in the column? Because the column
2
is
to the 64 numbers times 4.
Okay.
Each column is 2 to the 64 in length. And we have the proper code, by the way, if you need more than that, we will increase the offset by 8 if you sample enough, or if the sampling pattern is big enough that we will use 2 columns for sampling.
Okay. So then my follow-up question, and I think this is covered later in the doc, is isn't it very inefficient to only use one subsequence in terms of sampling space?
That is a question I will have for Natalia.
Yeah, we definitely cannot use only one subsequence. So if we move to Albin's proposal, we would need to carefully increment subsequences. Once we exhaust one, we will definitely exhaust one. 2 to the 64 is not a big number.
Sorry, do you mean that we need to make sure we go from one subsequence to the next, or?
Yeah.
Okay. Yeah, that is definitely what we want to do. Yes.
Yeah, because
That's
if you
why
just roll over the offset, then you'll start repeating random numbers, and that's bad.
Yes. Yeah. We will go like, once you finish subsequence, you go to the next subsequence. And that is why the proposed API adds a subsequence index that it does not have today. Today, we only have offsets. And the new API proposed to add a subsequence so that we can actually index exactly where you are in the middle of that big 2D matrix. And then you can sample linearly basically as many elements as you need, and you move the offset and the subsequence to the next unsampled value in that array. So that's the proposal. I think Natalia has quite a few very good points on this, and about the complexity of this new implementation, about the reliability, when parallelization changes. And I think it goes all the way back to what is the guarantee that we will provide. And I think a very good example that Natalia was mentioning is what happens if I have tensor that I transpose, and then I sample from that. So I don't have a contiguous tensor. So how do we define what is the order we're going to sample from the Philox array and fill the tensor itself? What kind of guarantee we want to do for that? And we can have more even weirder examples where you can have even non really contiguous things where I want sample from the diagonal elements or things that are weird.
Actually, I also have another example for you, which is if I'm sampling from the normal distribution, I'm typically going to do this with Box-Mueller, which I use 2 samples, but they get mixed in a different way to generate my samples. So like that's also going to cause you problems, right? Like if you want to give a strong guarantee.
No, I think Box-Mueller should be enough. We would just be distributing the numbers between threads, giving each thread 2x.
No, but like so in the intro, the thing was like if you sample 4 numbers and then another 4 numbers, you should get the same result if you sample them all in one go, right? But if I do a normal sample and ask for 3 numbers and then another 3 numbers, that will be different than 6 due to how Box-Mueller is going to do the sampling under the hood.
No, but in the first case, when you're asking for 3 numbers, you actually need to read 6 numbers from the sequence, and like 12 numbers if you're asking for 6. So I think Box-Mueller is not a problem. The problem is Poisson distribution that actually requires a predetermined number. It's sampled in a while loop, but we can forget about it for now.
Isn't the way Box-Mueller works is I do 2 uniform samples and then I use them to generate 2 normal samples?
Oh, you're right. When you are generating two normal, yeah, that would. You're right. Sorry, I was off on
But
this.
can't you generate two? Cannot you use two consecutive samples for each of these?
What I'm
Yeah,
just
you
saying
would
is that.
be-
Oh, go ahead, Natalia.
So the problem is, I think you can pull it off if you're generating the even number of normal samples, but if you have to discard one of your normals, then when you're concatenating two arrays of size 5 or one of size 10, because you're not discarding things in the first case, you'd be off.
So just concretely walking through this, right? To generate the first two normals, I sample two uniforms, and then I get two normals from those two uniforms. And then to generate the last uniform, I still sample to get the last normal sample, I still have to generate two uniform samples. This will give me two normal samples, and what I'll do is I'll just throw away the second normal sample. And then that's why it'll be offset by 1 when you do this. So my conclusion from this discussion is that we can give some more guarantees, but I don't want to give the guarantee that like if you sample separately versus concatenate together, you get the same thing. That just seems too hard.
Well, my general problem with this proposal is we cannot give perfect guarantees, and the imperfect guarantees that we can give require a lot of work. So to me, it doesn't look like a good trade-off between improved experience and the amount of work it requires.
One thing I would mention, though, is that if we want to create this functional API that matches eager without changing eager, this will make this new functional API a little bit more complex to do.
Okay, so actually, I want to step back a moment. So you have a motivation at the top of this document, but I don't think this is actually your true motivation. Like, as in, I think what you are asking for with your motivating example is too strict. So can we talk about what the actual requirements are?
It is, well, I think in the case of the distributed tensor, it is exactly their ask. Because this is the local sampling, and this would be the sampling onto.
No, but wait, this would work only if you are sharding on the outermost dimension. If you are sharding on the innermost dimension, which distributed definitely will do, then no amount of trickery that you are describing will help you.
And I've also argued to the distributed that they don't care, like they don't need the eager sample to match up with the sharded sample, because if the tensor is too big to fit on a single GPU, well, like how are you even going to know that the sample is different? Because you couldn't have like sampled it all on one GPU anyway.
So Natalia, that's why there is this stride argument here that you're gonna love. That is exactly here to solve that problem of what if you split on non-zeroth dimension. So that is covered. To Ed's point, yes, I agree that there is a scale where you cannot verify that, but it was still a nice to ask.
Yeah, but I'm saying this is not the real reason you guys are coming and proposing this right now, right? The real reason you're coming and proposing this right now is so that we can do activation checkpointing, right? So what guarantees do you need specifically for activation checkpointing?
For activation checkpointing, we only need that to match eager. And I think, I don't know, Animesh, I don't know if you want to give the context. My view of the context is Animesh was trying to implement that, and it was a nightmare to do it to match eager. And it was like, oh my God, what is happening in there? And after diving into what happens in eager, we're like, okay, can we simplify that story and make it generally better to get multiple devices to do the same thing, to make this new sampling function a lot simpler to use, and generally the system simpler.
But I guess I don't understand why it's difficult to implement. Like, so Philox RNG, well, is the problem that, okay, so rewinding a sec. So let me give a counter proposal, and it's bad for a reason which is very obvious, but I think it should work. So the counter proposal is, instead of trying to put everything through a single Philox RNG function, we just functionalize every single random number operation individually. And the way you functionalize them is you take in the offset and the state, and then you just, set the generator to that, and then you run the traditional operation in that case. And so my claim is that this would give you the same behavior as eager.
Animesh, do you want to answer?
Yeah, I think it does for
Yeah,
GPU.
and the obvious reason you don't want to do that is because there's a lot of random number functions, and you don't want to have to like do all of them again.
Okay,
So
what does taking the generator state mean?
well, so if the traditional RNG function supports a generator argument, then what the functional API does is it just takes in the offset, and then it creates a generator that like is got the state corresponding to the offset and the state, and then calls the regular API.
So
One flaw in this argument is that CUDA graphs don't support custom generators, so we'll need to do something about that.
Right, but that's sort of in principle solvable.
Yeah.
a couple of comments, Ed, which are most of our RNG, not all, but most of them end up calling RAND, by the way, in the actual backend. So we already do this kind of decomposition all the way to RAND. Anyway, the other thing
is that true? That's not true. What are you talking? Are you talking about decomps, or are you talking about our actual eager implementation?
I'm talking actual eager CUDA.
No. Like certainly they all end up sampling from uniform, but this is what like the template business is, right? Like we need to fuse the like transformations with the sampling, because that's like important for performance.
Yes.
So it's not an actual RAND call and then do some operations after it.
Oh,
right?
no, it's not. No. Yeah, it's a QRAND call.
Yeah. Okay, fine.
Also, our generator API is not Philox specific, meaning you don't get offset and subsequent.
Right. Yeah.
So
So like in my proposal, you'd have to like have a very specialized for Philox thing. Like I as I said, my proposal is not perfect, but like I'm just trying to like understand. Hey, like for the thing that you need, which is the functional API does the same as the mutable API. Like you don't actually need this.
No, that's what I was saying earlier. Of like, as we were implementing, as Animesh was implementing this thing, he realized that it is very much non-trivial to compute these offset and like to get the new states.
No, but my thing is not. I think my thing is pretty simple. So there is an annoying thing, which is you have to like extract out the offset computation for every kernel. But the way that works is you go read it until you find where the offset is computed, and you pull that out, and you've got to keep them in sync and stuff. But it's not complicated. It's just there's a lot of them you've got to do.
You don't try to recompute them. You just stash them when you use them for the first time.
Or yeah, you can do that too. Exactly.
Dries is having a similar problem for the low mem dropout for the transformer thing that he was working on. So actually adding an API that would allow us to stash and reuse offset and SID would be beneficial for those.
For dynamic shapes, though, I do need this to be symbolically traceable, the offset compute, because obviously it'll vary if you change the input size. Okay, we're at half past. Shall we take this offline? Maybe for the next meeting at 2?
Yeah.
Okay, so pivoting over to Preautograd, which was resoundingly voted for. Okay, let me think. Does anyone want to present this, or am I presenting this? Brian, do you want to present this?
I don't know what specific thing we want to talk about.
Yeah, okay. So, let me present this. So, I I should have taken notes. Okay, pre-autograd tracing. So let me think. So just to start off, I just want to briefly explain what pre-autograd tracing is. And then I want to open the floor for people like Michael who have potential use cases, and we can talk through them. And obviously, if other people have things they want to add in as stuff we should talk about, we can roll the conversation that way. But I think the good starting point is to just sort of explain what pre-autograd tracing is to set the stage. So what is pre-autograd tracing? Pre-autograd tracing is a new functionality that Brian added to our makeFX tracer. So our makeFX tracing says, given some Python callable, we'll convert it into an FX graph of A10 operations. And then there's also some control over decompositions, which say, hey, if you see this A10 operation, please automatically decompose it into more operations. And we usually, this is a thing, and the Python callable can have autograd calls in it, and that's how AOT autograd works. And the final thing is, one thing that a lot of people have noticed is if you have a what's called composite implicit autograd decomposition, it is not possible to prevent this decomp from happening. And the reason why it's not possible is rolled up in how makeFX is implemented. And I want to briefly describe this implementation because I think this is the easiest way to understand what pre-autograd tracing does. So the way makeFX is implemented is it interposes on our dispatcher stack. And our dispatcher stack is basically a number of layers of sort of subsystems which run one after another whenever you call a single operator until you hit an actual CPU kernel or a CUDA kernel. So a typical series of dispatch keys you would go through might look something like, first you do autocast, then you do autograd, then there's not much else. Then you do CPU, CUDA, or Python. And one more thing is that before you even get to the dispatcher, there's another step before that, which is the Python argument parser. And that's just what takes you from, torch dot, matmul into the dispatcher call, which will be like a10.matmul. And then by the time you've gotten past autograd, you no longer have a matmul anymore. You instead have something like an or something like that. So the way makeFX works is we run all of this stack until you get to Python. And at that point, we just see what calls have actually been made after you've finished processing all of these subsystems. And that's what we record to the FX graph. So pre-autograd makeFX says interpose before autograd. So what we will end up doing in that case is we will run Python argument parsing. We'll get to the dispatcher. We will do autocast, but then we will stop and record whatever calls that we would have made to the autograd layer instead directly to the FX graph. And that's it. Questions about this explanation? Okay, so with that out of the way, let's open the floor to use cases. So Michael, do you want to kick us off?
Sure. So the basic use cases for the new ads stack, we are using makeFX to capture the graph, and we capture it in two modes. So one, before we pass it to like a native runtime, we'll do forward backwards, and that allows us to sort of fully capture what's going on and plan and blah, blah, blah. We also want to be able to run in a mode with like a Python backend, where you kind of reuse all the existing stuff. So there we want to capture the forward only, and then we want to be able to call backwards on it just like you would call backwards on your sort of eager NN module, and for everything to work. Notably, things that don't work today are grad mode variables, like grad mode setters and getters. And there, yeah, Sherlock mentioned something about how we don't correctly preserve requires grad or something. Although this is not a problem in practice for ads models because there's only a single output that we care about in terms of calculating the loss. That's about it. So that's why I was kind of asking, like, do we actually? So today we actually trace, I think, Postautograd, the forward only. And I don't know what the difference between the post-autograd looking graph or the pre-autograd looking graph is, because we don't, it seems like decompositions, implicit autograd decompositions are the primary reason why you would want to turn off autograd for our particular use case, and we don't run any decomposition.
Dark Ritual.
I have a question on like when we say pre-autograd, to what extent do we want to say pre-dispatcher?
We don't.
Pre-dispatch functionality, to be clear.
What does that mean?
I think this is an
capture...
orthogonal question. Is that true, Alvin?
Yes, it's more for your intro. Sorry.
Okay, so let me just answer Albin's question first, and then let's return to Michael's thing. So I do not mean pre-dispatch, because, for example, and I believe this is true for Brian's implementation. Brian, please correct me if I'm wrong. I will get autocast when I do a pre-autograd trace. So the autocast stuff will get inserted in. And if I didn't want autocast to be applied, then I should have done a pre-autocast trace instead. And in general, there's basically n different tracing modes, one for anywhere you put it in our particular stack.
Okay, so this discussion is really about pre-autograd and not of the other pre.
We can obviously change it, but unless someone is very interested in how automatic mixed precision interacts with this stack, autograd is sort of the main thing that people are interested in.
Sounds good. Thanks.
Okay, so returning to Michael. So did anyone have any other questions or responses to Michael's?
Yeah. Well, I mean, there's other stuff. Or I guess I'll comment one thing. I wouldn't be opposed to a pre-dispatch trace. If that's I wouldn't be opposed to a pre-dispatch trace. I think so when we're talking about what we want here, my view is, or what is not sufficient about the current Dynamo post Dynamo pre-AOT autograd representation. And I think the biggest one is just that it's torch operators. I guess actually I think that's the biggest one. It's torch operators, and also actually I would say that's the biggest one. And so I think the main goal.
Wait, Horace.
Yeah.
Isn't the allow and graph thing a bigger issue there?
Allow and graph is also a big issue, but that's kind of a separate topic, I think. I guess we can talk about allow and graph, because one of the things that I think when we're talking about the use cases for pre-autograd representation is that if we want to export it, for Michael Stroh's case, what this implies is that we need to have a standardized representation for everything in the graph. And in particular, things that might be in the graph that we currently do not have any good solutions for are checkpointing, as well as anything else that we might apply allow and graph to, such as autograd.function calls. And so that kind of ties into higher order operators, but perhaps that's another discussion.
Richard?
In favor of pre-dispatch trace, it sounds like what we want we don't exactly want a pre-autograd trace. We just want some trace that can be rerun with the same semantics as just running that code in regular PyTorch mode. So concretely, this is what they have in JAX. JAX's equivalent of makeFX is called makeJaxper, and you can just rerun it, and it gives you the same exact semantics as if you had just run it without tracing. And the way they sort of the way they do their lowerings down to XLA is that they just have a separate phase where they are able to take their trace and get rid of the stuff that pertains to transforms before they just straight up lower it down to XLA.
Okay, so I'm going to accept this. So we're calling this now pre-dispatch tracing, and it now interposes before all dispatcher keys. Brian, that's an easy change to make, right?
Yeah.
Can we sorry, don't know what this means. So like what would be different about the graph that's pre-dispatch versus pre-autograd?
It would have autocast in it plus some other things.
Yeah, like autocast would presumably be like a higher order operator of some kind, as opposed to a like just baked into the operators.
Okay. Okay.
That's one question I had around.
I'm
like,
not sure which I want, but okay.
Like maybe an orthogonal goal of pre-autograd tracing that I hear people talking about is it can be nicer to write graph transforms on a pre-autograd graph than a post-autograd graph. And like one reason I've heard for that is because you write a pattern matcher that matches some pattern you want to optimize. And if it's on a post-autograd graph, you need to worry about your pattern matcher working on the forward and the backward separately. And if it's on the pre-autograd graph, like hand wave, but you can match up once and the backward works automatically.
Well,
and
Brian,
like,
let's not conflate forward only, forward backward with pre and post autograd, right? Because you can trace a forward only graph post autograd or pre autograd or pre dispatch or whatever.
yeah, I feel like they're two separate problems. So I guess I'm just talking about the like someone writing a graph transform problem. And it's not clear to me if when someone says they want to write a transform on the pre-autograd graph, that it's necessarily easier. Because you have all these extra things in your graph, like higher order ops for autograd or higher order ops for autocast.
It's not like I would say it's not easier, but like sometimes it's kind of, or like in general, like I would expect that like, you know, just a base transformation, like a base graph transform is harder on a pre-autograd graph, but like if you're accounting for the fact that you also need to deal with autograd and things like that, it can be easier. So for me, a canonical example here is if you want to pattern match flash attention, this is quite difficult on a post autograd graph because you need to like both pattern match like your matmul, softmax, matmul in your forwards pass, as well as what's going on in your backwards pass. And then you need to like, you know, save a different thing compared to what you were previously saving. And this just sounds like a disaster. And actually, I'm not even sure it's feasible. Well, if you're matching it on the pre-autograd graph, all you need to do is just find like the matmul, softmax, matmul pattern. And then you can just replace that with like a flash attention kernel. And then when you do autograd on it, it you know, gives you what you would expect.
Well,
but isn't this sorry?
Yeah, sorry. I feel like we really haven't defined the motivation for this thing. It's so we're going into the weeds of like different proposals for what it can do, how to do it, but what do we actually want this for? I've heard one thing is like one thing I did hear the graph transform thing where people wanted ways to do transforms on ops before autograd decomps. So basically it's to avoid these composite decomps is the problem in that,
no, it's not case. Avoid, or like I wouldn't define it as like avoiding composite decomps. It's avoiding like needing like it's like after you do autograd, it's like decomposing things further. And if you want to like do something to this whole group of operators, you're basically needing to recompose the structure that's like additionally added from autograd.
Yeah, isn't that the same as avoiding those decomps?
No, because there's also just like you have matmul and that got turned into an call and stuff. Even if you were tracing forwards only. So like Horace's thing doesn't exist if you are tracing a forwards graph only and you're not running backwards on it. So it does make sense to keep these as two separate use cases.
I'm gonna give a precise example about like it's not necessarily just about composite implicit. Like imagine you just wanted to replace matmul with special matmul or something like that. Like if you wanted to pattern match on the pre-autograd graph, it's very simple. You find the matmul node, you replace it with special matmul. But on the post-autograd node, there are at least 3 matmul calls. Both your forwards as well as the 2 matmuls responsible for it in the backwards. And you need to pattern match all 3 of those in order to like replace it with your special MM and special MM backwards.
So concretely, you're saying that like we don't want people to do transforms, like graph transforms on both the forward and backwards graph, and it's easier to do it on just one graph before we get to the point where we have 2 graphs.
Yeah, like in cases where you want to do a transform that has ramifications across two graphs, like in case where like you want to do a transform that has like that wants to like interact with both the forwards and backwards graphs together, it's much easier to do it on a pre-autograd graph. And to be clear, there are still transformations you might want to do like on the post-autograd graph if you don't care about like the interaction between the forwards and backwards, such as like operator fusion and things like that. But there are some transformations that are easier on the pre-autograd graph.
Okay, so then I feel like if we want to expose a place to do transformations, I'm convinced that this is a better place to do them in some sense, but it's not well defined, and I think it needs to be well defined. Like if you want to have an exit point to do transformations on, we should be able to say what the IR looks like at that point. And I don't think I buy that it's torch ops, because it isn't if you have allowing graphs or call modules.
Right.
Like
so
that.
sorry. Let me just put some more clarity on this. So Will, one more thing people want this for is just torch to A10 op Python argument normalization. So this is just torch supports a lot of different ways of calling operations, and that's annoying. Let me just talk about how this interaction interacts with allow and graph. So recap, allow and graph is a thing that lets you say, hey, Dynamo, don't attempt to Dynamo trace through this. Instead, just pass this on directly into the FX graph that I'm going to send to AOT. So allow and graph has no interaction with makeFX, right? makeFX does not do anything with allow and graph. So with a pre-dispatch tracer, we will trace through the allow and graph block, and you will not see any allow and graph blocks in the resulting Dynamo graph.
I think I have a different opinion there, which I think basically allowing graph should just be banned for the cases like Michael So's where you just want to export it. And like, yeah, otherwise than that, you just kind of ignore it in like the eager mode kind of situation. Because I think like if you're like the point of a long graph is that Dynamo cannot capture your thing. And so the only thing we have to rely on is like makeFX. And I think makeFX through allowing graph without Dynamo is kind of a risky proposition to me. So imagine you just have an autograd function. Actually, maybe we can make that work. Yeah, but like I guess it seems like riskier to me. And so like I would just say that like allowing graph like in the exported IR is just like you can't use it if you want to like export a pre-autograd trace.
Dark Ritual.
I don't think that's gonna work for us though. Like, what does that mean in practice? Like, we use makeFX to capture the graph. Does that mean that we can't capture like pre-autograd? Like, I don't even know. See, we keep talking about pre-autograd. Like, what I want, like torch no grad. Like, what do I get?
No, it doesn't matter if it's pre-dispatch or pre-autograd.
Okay.
Like in all of these, if you just allow and graph, it will evaporate once you makeFX it. If you don't want it to evaporate, then you want Richard's custom op API. Like, and if you think that's confusing, then we could say, okay, maybe we need to rationalize custom op versus.
Wait, why do I need custom ops for torch no grad support?
No, you don't. It's just I was talking about the hypothetical where you wanted the allow and graph to get preserved because it's allow and graph, right? So you're like, oh, that means it should show up in the graph. But the answer is no, that's not what it does. What it does is specifically keep it in the Dynamo produced graph with no guarantees for whatever happens afterwards.
Oh, I see. So we're just okay. So this is just like a Dynamo.
Well, this is sort of like a nomenclature UX thing mixed up with like specific mechanisms going on here.
Terrible name. We should rename it Traceable or something.
Dark Ritual.
So let me use the pre-autograd terminology for this example. So like going back to what Horace was talking about where, okay, I want to make some change to the forward graph and I want it to be picked up by the backwards graph. That's sort of like what fundamentally seems important to pre-autograd rather than like whether decomps are running, which is a little orthogonal. Okay, so take that use case. Now, what if you want to manipulate the graph in such a way that like the built-in autograd won't know what to do? Am I just stuck and I have to go back, or can I like insert my own custom op or something? Like, I don't actually understand how this works end to end.
I can try to answer this. So let me just make this very concrete. So you want to change your matmul into a special matmul that you don't have an autograd formula for. Does that sound like what you were talking about? Okay, so you have a few options. So one is, well, you know, you can just run it post-autograd. And obviously that doesn't work if matmul's getting decomposed by a composite implicit. But then you could, for example, use Richard's custom ops to make sure that it does get preserved in that case. You could also just do it pre-autograd anyway and hope that someone doesn't try to actually call backwards on your thing, right? If you're doing a forward only.
But the general thing is I would use the custom op thing, set up my own custom op, and then run it. Is that right?
I mean,
Wait, sorry, it is like a mammal with like this mammal is not like a composite op, right? It's just like a new mammal.
That's right. Yeah.
And so it has like its own custom backwards formula that is composite. Correct. Or composite. Well, I mean, and then I think in this case the answer is like you needed a final autograd formula for that operator.
Yeah, but what do I?
Yeah, and you do that by defining a custom op.
What do I stick in the custom in the forward graph? I stick my custom.
You stick your custom matmul forwards, right?
Okay.
Yeah, that seems fine. Okay, so I want to return to Michael Swo's original point. So what's the difference between the post and pre-autograd graph? So to answer that question directly is the pre-autograd graph. Yeah, let's forget about autocast for a moment. So the pre-autograd graph, composite implicit autograd has not been applied. And set grad enabled, disabled, and the similar higher order ops are still in the graph. Those are the main differences.
This is if I do pre-autograd.
If you do pre-autograd, as opposed to post-autograd.
Okay. And okay, so and pre-dispatch question.
Pre-dispatch would be the same unless, well, I mean.
Wait, sorry, I'm gonna, I think, rephrase it a different way. In that, like, in particular, like, I think the guarantee you kind of want from this, like, I'm gonna call it pre-dispatch, like, trace, is that you can change the, like, gradientness or general subclassness of your inputs, and it is, like, it correctly, or, like, you can change, like, the gradientness of your inputs, and it still matches what eager would have done.
Gradientness meaning required gradness?
Yeah, required, like whether it requires grad or not. Because like basically the post-autograd, or so.
Okay, I don't know why you would put it this way, Horace. This is not helpful to me.
I mean,
helpful to me.
Well, so like, okay, another way to explain it is essentially once you've run a subsystem, like, unless you are doing PyTorch style, like, nested stuff, which you usually aren't, you no longer get to change the decisions made by that subsystem, right? So once you're past autograd, you don't get to, like, change your mind about, oh, actually, I wanted this to require a grad or not, right? So by doing a pre-dispatch trace, you basically haven't run any of the subsystems yet, and so you can change them all out however you like, and then run them later. Once you've run the subsystem, you're sort of not allowed to change it anymore.
Okay.
That
does make sense.
What I'm missing, sorry, is where are you changing the subsystem, Michael?
So in this case, it doesn't matter because like we're just gonna do the exact same thing. So I'm not actually that sensitive to do we do pre or post autograd because I'm not gonna change like the gradness of anything or anything. But I do understand now, at least like infrastructurally, why it would be nice to be able to draw this line, because even if, you know, we don't change it, you know, so I understand the infrastructural reason, although it happens to be the case that in this use case, I don't care. And also like ad models don't use AMP. So like, you know.
One thing, by the way, here, Michael, as well, is I think things like the partitioner, like what goes in the forward, what goes in the backward, also happens here. You cannot change it anymore.
Well, so in this case, the specific use case I'm talking about here is where we only capture the forward because our plan is to run the backward in eager.
But like, isn't the distinction not whether you are changing something, but whether the subsystem is like independent or whatever? Like whether you can rerun the subsystem? Because if you're not changing anything, then saying you can't change anything like doesn't have any meaning.
Well, that's what I'm saying. Like for us, I don't think it makes a huge difference. So like concretely, what we currently do in the ad stack is we capture post-autograd, but I like hack in the like the setgrad enabled calls as just side effecting ops, and that works okay
because they've been removed by the subsystem itself.
It's because makeFX doesn't trace them today.
But even if it did trace them, it should remove them after running autograd because they do nothing after that.
Yeah, so like what I'm doing is actually like a layering violation, basically. So that's why I was saying I understand now, like, okay, it wouldn't be a layering violation if we did a pre-autograd, and that's cool.
Raziel?
Sorry.
Yeah, I mean, I guess just channeling Will's question, how will we explain this to user? Is this something that you're gonna try and see if it does what you want it to do, and then great, or right, like, can we actually put a contract that is, you know, somewhat like actionable by somebody without having to go and trial and error? Like, for example, for Horace's case, right? Like, I understand the use case, right? But how can somebody go and know, oh, right, like, this is what I need to do because this is what I want to do. And basically enabling this feature is what will allow me that.
The way that Richard put it, or maybe it was Horace, I don't remember, where it's like the pre-dispatch guarantee is kind of like what you ran. It's like the same as what you ran in eager. Actually does kind of make sense to users, because then it's like, oh, when I'm running a transform, I'm running a transform of basically the eager code, right? And that's the guarantee. I don't think any of these like finer gradations, like post-dispatch but pre-autograd or whatever, like make that much sense. It's basically like, do you want like the whole subsystem involving like taking eager and like spitting out the autograd graph to have run or not, right? So this is kind of pretty coarse.
The decombs matter, right? Because it affects what shows up in the graph.
Okay, that's true.
Like in the IR. The other things probably don't matter because people won't care. But...
Yeah. Or so like I would like another way I would maybe phrase this is like I feel like this is equivalent to like what fx.symbolic trace gives you in.
But it's not, because fx symbolic trace doesn't normalize.
Not literally, but in terms of how users deal with it, like it's just like it's happening before anything in the C++ dispatcher. And so we're like the kind of outcome it seems like we might like one outcome we might get from this meeting is that we want to define like a clearly defined IR at that level that you can work with and deal with.
Raziel, Greg, any more comments?
Yeah, I mean, I guess the only thing is that, right, like basically what we're saying is we're basically disabling or bypassing very complex subsystems, and it's really hard to tell you, right, like summarize what is that you can expect out of it. So you have to go and try it out. Is that basically?
So let me try to like draft out this contract right now. So the pre-dispatch FX graph contract. So what ops? You will see canonical A10 ops. You will also see some more A10 ops. Those will typically be the ones that like got obliterated by composite implicit autograd. So you can pull up that list by just looking at what ops are composite implicit autograd. You will also have funny extra like metadata subsystem control ops. Right? So for example, you may have an autocast higher order op. You may have set grad enabled, true or false, or changes to requires grad, or no grad, high order op.
I would also prefer for those to all be high order ops. Yeah.
Okay. Preferably all high order.
There is also enable disable determinism.
Sorry, enable disable
determinism.
But essentially, for any subsystem that you didn't run, there will be ops associated with it that will control the behavior of that subsystem. And that's it. That's the contract. Greg?
Pura streams and devices also.
I was just going to ask, so it seems like there's kind of the two similar, but two different use cases. One is the traceable pre-autograd, so you can run your autograd later and you don't care about transforms. The other is the you care about doing a transform before your subsystem case. And my question is, how useful is this feature without functionalization? Do we need to land? Do people want to have a pre-dispatch graph that is not functionalized, or is it basically useless unless you also get a functionalized graph?
Horace would say it is still useful. You have to be a lot more careful. Oh yes, so that's the other thing. Mutating out ops will appear in the graph. And so the answer is it's harder to write transforms, but it's still useful if you are willing to deal with handling all of this correctly.
And in your subsystem control ops, you have the functionalization control ops, I guess, as well.
But how are you going to handle systems correctly? Because functionalization is different kind of correct. It's difficult to handle correctly. Even that softmax pattern matching, FHMA pattern matching won't be strictly true if something else is happening non-functionalized with your inputs or outputs.
As I said, you have to be very, very careful. Dark Ritual?
Oh, that's it. Sorry.
Okay. We are over. Any last comments before we break? Okay. Thanks, everyone. See you all next week.
See you guys. See you.